Going. There we go. All right, a couple updates to schedule, at least in 9 a.m. we didn't finish homework 3, so I just pushed it off so we can get one more day, finish up the last 2 problems that we've been working on, which kind of pushed back a few other things like quiz 3. We need time to actually talk about what should be on the quiz, so we'll do that Friday. So today, Wednesday, do some more problems. Friday, talk about what we want to show for our knowledge. And then next week, work on the project. So looking at like pendulum solutions and like what that means, like how to use different equations of motion and how to solve different stuff. And then we'll jump into, and I'll have to push off like homework 4 because it probably shouldn't be done after like 2 days of like thinking about it. But anyway, we'll get there when we get there. Right? Cool. Sound like a plan? At least for the next couple of days, week out. No issues? Yes issues? No issues. Cool. All right, we were working through, I think we got through 330. Now we're looking at like 334 in the textbook. So I copied it in, at least part of it, the question, and kind of drew out. I thought it was important to have a red balloon, and we want to find, the main thing here is like, what is the equation of motion for this balloon? And the first thing that we're told to do is sketch a point mass model of this balloon on a string. What does that change about the motion that we're modeling for this balloon? Like if we say that it's a point mass rather than like an actual, because a balloon is not a point. It's not a singular point. It's got some kind of momentum. It's got angular momentum. So what does it change about this problem if we say that it's a point mass at the end of a string? Yeah.
So like you said, it has the balloon itself has like an angular momentum and stuff like that.
Yeah.
So making it a point mass kind of negates those calculations.
Okay. Yeah. So what is that? Like, what do we lose from that if we say that there is no angular momentum in the balloon? The balloon itself. I mean, we can say it has it as it's moving around on the string, but what do you think?
Can you repeat the question?
If we take this big red balloon and say that it's not a big red balloon, it's actually a tiny point at the end of a string. And now I don't care if it rotates or if it doesn't rotate. What am I losing from that?
Degree of freedom.
1 degree of freedom. Yeah, so there's 1 less degree of freedom, which is kind of nice. Usually we want less degrees of freedom. It's just easier to kind of model it and create equations of motion. So there's 1 less degree of freedom. Have you ever like watched someone carrying a balloon? Like if they're walking one direction, then they change directions and start walking the other way. What happens to the balloon as you're like, or as a little kid is like yanking it all over the place? What's happening? What is the balloon doing as the string keeps getting yanked this way and that? It's wobbling? Yeah. So like we're never going to have a situation like this, right? We can't, because it's not going to be part of our model since we said that it's a point mass. So we can't say like, oh, the string yanked on it this way, created torque, and rotated the balloon. Because we're saying, no, I don't care about that. We're just looking at a point mass solution. And that's okay. We can do that. We can do whatever we want. We could say this whole thing is just a balloon on the ground. It's a model. It might not be accurate, but we can do it. All right, so I know it's like do 3 things before a free body diagram, but I just want to look at what does our free body diagram look like. So we're going to use a little point mass to describe that free body diagram. What forces are you going to add onto that free body diagram? And where are they pointing? What does it look like? All right, cool. I'll grab like stuff that I saw so far. Kind of like some kind of buoyancy pulling it up off the ground. It still has, even though the weight might be small, it does have weight pulling it down. It's just buoyancy is bigger. And then tension. Tension, in this case, it's a constraint force, right? Like, it's not that tension's always going to be 10 newtons. It's just, it has to be whatever it needs to so the balloon doesn't float away. So it's always there, we just don't know what it is. So gravity, buoyancy, those we know, but tension is a constraint. All right, so we did this one and we did that one. And now, really this like derive the inertial kinematics of the balloon. It's just like draw the kinetic diagram is really what it's telling you to do. It's like the inertial kinematics is describing like what is that kinetic diagram. So that's next question. What kind of coordinate system are we going to use? Polar? You want polar? Yeah. So we could use polar and say that this is our origin. Is that right? Sorry, at the bottom. So if the balloon was r equals 0, it would be sitting on the floor down there. If theta is 0, then it's straight up and it's right there. Like this. At least this is how I would draw it if I'm choosing polar coordinate. It's saying like right-hand rule, as theta increases, it moves counterclockwise. Busy today. Yeah, a lot going on. So with polar coordinates, we can take acceleration, like there are definitely two components of acceleration. Like we can say that it's an x and a y, we can say that it's two other things, but as long as they're 90 degrees to each other, if we're using polar coordinates, what do they look like? Where are they pointing? Like where are those arrows pointing? So I know that there's some kind of like total acceleration is something like this. How am I going to break up? Do I want components like that? Do I want them like this? What are the two A component, A1, kind of like component 1, component 2? Where are they pointing? So that's what we're trying to do right now. Is what is that kinetic diagram? What does it look like? So it should be.
So one of them points towards the center, towards the origin.
Towards the origin?
Isn't that how it's isn't that this definition for something moving in a circular motion?
If you want to use an inertial frame of reference, then that one would have like v squared over r towards the center, and then like a dv dt along the curve. You'll end up with the same equation motion, but now you're talking about v instead of theta.
So right now, are we working out like a new coordinate frame?
Yeah, so if we say that it's a polar coordinate frame, and we have like r and theta, r is like magnitude of position, and then theta describes direction, where it is. So then it'll have some kind of radial and theta acceleration, and we want to know where it's This one, when you're creating the equation in motion, really what we're doing is describing what is the equation that's going to be true all the time. Whether the balloon is over here or straight up and down. Is that true, like if you're spinning something on a string?
This doesn't change. So it's just
But it does have tension in the strain, right? Because then the tension is acceleration. Even if there's something here in this case, like we have changing speed and changing
because like but like since the opposite there's no
well, we have like part of the buoyancy, part of the gravity are aligned. They're not aligned with it. That's why there are components of gravity and buoyancy along that. Because they're not like 90 degrees. If it was 90, then yeah, 90%. Only tension not sure. Yeah. Okay. I mean, we didn't add like whether or not we could say like right there's this restriction, but there's really All right, so with the kinetic diagram, I know like people are trying to look at the free body diagram and figure out like what is the resulting kinetic diagram. But really, can I block it out? I don't know if I can. Yeah, anyway. But really, I could just ignore that free body diagram and say, look, I chose a polar coordinate system, and I know how to define acceleration in a polar coordinate system, because the fact that there's buoyancy, the fact that there's tension, like none of that really matters when I'm just trying to say this is acceleration. In the same way that like when we have Cartesian coordinates, there is an acceleration in the x direction, there is one in the y. Sometimes one of them is 0, sometimes one is g, sometimes one is like friction or something, but it doesn't really matter. The kinetic diagram is just describing like when momentum changes, what is that effect? So in this case, I'm gonna come back up and look at like if this is my radial direction, so if the balloon moves away, then that would be ER, but it can't. So R is constant, so I have that like R constant. If I increase the angle, that's describing E theta. That's describing like which direction is an E theta. So an increasing angle is saying this way. So I'm going to have two components of acceleration. One is radial, just describing like, is it moving towards the center, like towards 0, or is it moving in a circle, the theta? And it can be both, right? Like you can have two components. Nothing. So got this MAR and then MA theta. And that's it. Like we're not trying to figure out like what those components are. We're just trying to say this is a positive acceleration radial. This is a positive theta. Yeah.
Why is the left side picked as like the positive for E theta?
Yeah, like y left positive for E theta.
Just either one.
It's not either one. This one. This one, I like to maintain that counterclockwise is a positive theta. So if I want to say like E theta as a positive, like counterclockwise, increase that unit vector to point in a circle going counterclockwise, then I have to say that it's pointing to the left. So even if I drew the balloon like on the opposite side, really I'm saying it has a negative angle, and if it moves to the left, I still have like a positive. I'm increasing the angle to get back to 0. But to answer your question, like could I have done the other way? Like yes, but now you're using left-hand rule, so keep track. You just got to make sure you keep track of positive, negative values there.
What was your notation? MAR and MA?
This is MAR, and this one MA theta, like the radial acceleration and the theta acceleration. And let's do this. So when we have polar coordinates, we can look up the definition, you can derive the definition, but it's always the same. Like if I'm trying to describe motion with r and theta, acceleration is always this set of two equations, some radial component, some theta component. Some of these are 0, not the sum of them, SOME, just a few of these things are 0. So try to write this down, cross out the things that are 0 in this case for our problem. So we're crossing out whatever's 0 in our two like polar acceleration terms. What do you think? Its radius is constant. Yeah. The dots are like d dt. All right, this is what I saw. Take those two terms, cross them out. Why can we do that? Because, yeah, so we have R is constant and it is L. So anytime we see a dr dt, so that's what the dots are, dr dt, and double dot is d squared r dt squared. So those all disappear, and then we're left with just those like r and theta dot kind of terms. Cool. All right. So we chose the coordinate system. We know like we know what a change in momentum looks like. And again, like we can define AR and A theta without knowing anything about what forces are involved. So even if we change our free body diagram, like we were talking before about like what if there's wind blowing on this, and that's what's keeping it at that angle. We could add that in, and it does not change these definitions, like our definitions of inertial kinematics, which is a fancy way of saying like what is MA. So now we're at this step. We want equations or equation of motion. How many equations of motion should we have in this? 2?
I feel like it would be 2.
Feels like 2. 2 makes sense because we do have r and theta, and we do have a point mass.
What about like moment equation?
We could use a moment equation here too, but it won't change like how many degrees of freedom we have, or sorry, how many equations of motion. I gave away an answer because my next question was how many degrees of freedom do we have in this problem? 1?
It's only
Yeah, because so first off we said this is a point mass, so we took, it was like a balloon, we could say it's a rigid body, so there's x, y, and theta, but we said theta don't matter, so now we just have x, y, so 2 degrees of freedom. But then we said r is always constant, that r is always equal to L, so that's 2 minus 1, now we have 1 degree of freedom. How many equations of motion does a 1 degree of freedom system have? 1? Yeah, degrees of freedom. This is that one. That one you should always remember. The number of equations of motion is equal to degrees of freedom. So if there's 1 degree of freedom, we can only have like 1 equation of motion. But you're right in the sense that there's still going to be 2 equations. Like we're still going to end up with, we have a vector equation and we're saying F equals ma. We're still going to have like an R equation and a theta equation. Actually, let's just plug this in. M times negative R theta dot squared. This is like my E R components and my E theta components. So I have R, like radial components, and theta components. Which forces, because now what I'm really trying to do is say like F equals ma. So I know what ma is. What are my forces in the R direction versus the theta direction? We can start with 1 to help to like break it down. So what's my like R forces? Which ones are pointing in the R direction? Mg? Oh, tension, sorry. Tension? Is it trying to increase the radius or is it trying to decrease the radius? Decrease, right? So we have a negative T. Cool. If we want, we can simplify. We can kind of take that we have a 2 mg pointing up and an mg pointing down. Do you want to combine those? Makes it, then there's just one less thing to worry about, right? So then I can just say 2 minus 1 is only 1. All right, so now what do we know about that mg? Got to do some geometry for this one, right? There's got to be some component in that theta direction, some in the R direction. So I'll do. So if we have mg pointing up, our string coming down, that one's theta, this one's theta, and that one is theta. And again, like fancy high school geometry fun. Label the congruent angles in this problem. So what do you think? Do we have radial cosine or radial sine? We have like an mg cosine component and an mg sine component for theta. We're trying to find those two little.
MG sine theta is the theta, theta one.
In the theta?
Yeah.
Okay.
And the other one is cosine.
Mg cosine. Is it trying to increase the radius or decrease the radius?
Increase the radius, decrease the theta.
But it's trying to decrease theta. Okay, nice. All right, so this one's going to be plus mg cosine theta, and then this will be a negative mg sine theta. How's that feel? So far, seems right. Seems like we're doing something right. So we did all the hard like engineering work of like what are the forces involved, how do we want to model this, how do we add constraints, what coordinate system, all of that is kind of baked into these two equations. So the last step is what is our equation of motion? Like what is describing this system? How do we describe the motion of this system? I just want to check in and see how people think about that and approach it. That's a good question. Yeah. So usually an equation of motion, at least for all physics problems, because F equals ma, we have some second derivative differential equation, and that would be like our equation of motion. But sort of no matter what the system does, like wherever it starts, wherever it ends up, there's some differential equation that's always true. Yeah. So that's what we're trying to find here. You can have two. You can have, I mean, if you have 100 degrees of freedom, you can have 100 equations of motion. 1 degree. Well, 1 degree of freedom, you should end up with one equation of motion. Yeah, every equation should have some second order equation that says this is sometimes they're like in that swing pendulum, the bouncing and swinging, we have two equations of motion that are data order. That's okay. Radial? Okay. Or add together. Okay. No. Not afraid to commit to. Yeah. Confidence first. I mean, R is constant, so we could try to set it up like that, but then we would have one equation. You have data okay. Because we wouldn't have to.
Oh, I think we looked at the text.
Like if this was spring of gas, then we would have in this case, it's adding changes to it. theta and r, but r is constant. Do we have like a general stuckness? General stuck? Yeah. All right, so where do we want to back up to? First off, what is an equation of motion here? Like what are we even looking for when we say this is the equation of motion? Not sure. That's okay. Yeah.
It's related to the F equals MA, but it's always true.
Yeah. So since F equals MA is always true, like it doesn't matter what the initial conditions are or what happens over time, the equation of motion is stating this is F equals MA for all time. Like this is what's happening. So like let's back up to like if we have a spring and a mass, the equation of do you know what the equation of motion is for this system?
I know that F equals kx is the force.
Yeah, F equals kx. So we know the sum of the forces is a negative kx, because if I try to push it to the right, I have a negative that way. And then my MA is just x double dot. So my equation of motion for a spring and a mass is x double dot is negative km, k over mx. And because we always say F equals ma, and ma is our second derivative, we always end up with a second order differential equation. So there's always some kind of like double dot thing equals whatever the x's, the x dots, maybe a function of time, maybe a constant. There could be all sorts of, there could be whatever we want to add to it. So when you're looking at ER and E theta, which one has two dots in it? The theta component, right? So I can say my theta component is theta double dot equals negative G over R times sine of theta. And I'm not trying to like take the ER component and add it in there. I'm just saying this is going to be true no matter what angle it's at, and for all time. At least based on the forces that we have drawn in our system, this differential equation is always true. Kind of nice when the math is like, at least for identifying an equation of motion. Sometimes you have to do a little more work, but all right. So if that's our equation of motion, what is that ER thing giving us? Like, why is it there if all we need is the E theta component? So with once I have an equation of motion, I can integrate this twice, and I know what is theta as a function of time, theta dot as a function of time, and theta double dot. And I could take as many derivatives from there as I want, but I have like theta. I know everything I need to know about where this thing is, how fast it's moving, because I can find like some function over time. So what is this? What's this other equation giving me? Yeah.
Since it only has like theta dot in it, it's just like the change rate of the angle.
Rate of change of the angle. Yeah, it's giving us something that's directly related to the rate of change of the angle. Yeah.
Solve for tension now.
Now I can plug in, so if I get a solution for theta and theta dot, so theta's here, theta dot's here, I can plug that in, and now I have tension as a function of time. Since theta's a function of time, theta dot's a function of time, theta double dot's a function of time, like all this stuff. So now tension, I can say that this is, and we weren't really asked for this, but it seemed like people were kind of thinking about, what do I do with this equation? That ER component is giving you, like, tension was some unknown force, and I didn't know what it was, but now I do. I can say that tension is, once I find theta, now I know theta dot, now I know theta double dot, so I have a direct way to calculate how much tension there is.
So the tension equation is one of the equations of motion?
It's not an equation of motion, it's a constraint force equation. So it's telling you.
Oh, okay. So since there's only one degree of motion, there's only that one equation of motion. But this
Yeah.
is extra helpful tool.
Yeah, so since there's 2 degrees of freedom and 1 constraint, I end up with 1 equation of motion and 1 equation describing the constraint force. Sometimes a constraint force is just like a constant value. Like in the case of this like spring and a mass, the constraint force equation is just N equals mg, that it's just a constant value. But in our case where we have a balloon on a string, if you think about like bring the balloon all the way down to the ground and let go, for that initial theta equals 90, there's no tension in the string. And then as it starts to move up, it's moving faster and the chord cosine's getting bigger. Now you have more tension in your balloon string. Super fun. Cool. Masters of motion now. Then we only have 2 minutes, so we're not going to try to get through a whole nother problem. At least I don't think. I don't want to start it and you're like, no, cliffhangers. Yeah, too frustrating. What do we think? Other questions? Cool. All right, then we'll wrap up homework 3 on Wednesday and then talk about quiz 3 on Friday. That's the plan.